I am Qian, and I'm in my second year of PhD studies at the Monash University Math Department. And my research focus is optimization problem, specifically like some related to routing problems. And today I'll be presenting on a topic that we have covered in our submitted paper, the agricultural spring vehicle routing problem with splittable age demands. Oh, I'm really lucky to have the guidance of the fantastic team of supervisors, Andres, Rodolfo, Simon, and Philip. Okay, thank you. And okay, something happened. Okay, my talk is divided into 5 sections. Firstly, I will start with an introduction and motivation. And here I will discuss the reasons why we are researching this topic. And the second section is a problem statement, where I will define the problem and what we aim to solve. And the third section are models and methodologies. Will cover the different models and methodologies that we have used to tackle these problems. The section of results will present the findings of our research and how we have evaluated the proposed models and methodologies. And lastly, I will discuss on our ongoing work in the final section, providing an update on our current research progress and discussing the possible future direction for our work. Okay, let's move on to the first section. I'd like to begin by sharing some interesting statistics with you. According to the Agriculture in 2050 project, the world population is projected to reach approximately 9 billion by 2050. As a result, for production will need to be increased by 25 to 70% in order to meet the expected demand by 2050. And it has been estimated that the use of agrochemicals can prevent up to 45 of the world's food supply from being lost. And for agricultural chemicals, the robotic sprayer offers a sustainable and human-friendly way to perform the spraying operations in orchards. And with increasing orchard size, the time needed for spraying operations remains constant, and making it impossible for human workers to complete the task within a limited time frame. Consequently, robotic sprayer have gained popularity for achieving the spraying operations like in orchard, in some farmland, and some agricultural areas. However, there are few commercial path planning solutions that exist in the market. So to address this problem, our research aims to identify the optimal path for the agricultural spraying problems. Okay, so let's look at the problem statement. Here is an example of small orchards based on the attribute of real-world problems. The robot starts from the depot and then to do the spraying work for the blue dandelion. Subject to the robot's capacity and the age demands of the orchard, and every blue dandelion must be covered at least one robot. But actually, it is possible to have more than one robot to cover a single line, And the robotic sprayer are refilled at the depot when they run out of the agrochemicals. And in summary, we have some input parameters like a fixed depot over here and a robotic sprayer. We have same start and end vertex. And in our problem, the same start and end vertex is the depot. And we have age cost equal to the age length, and the age demands equal to the required the amount of required agrochemicals. And the rules is, first of all, the sprayers is refilled at the depot when running all of the chemicals, and we allow splitting the demand on a single demand edge among robots, which is mean that for single demand edge, it can be served by more than one robot. And our objective is to minimize the distance travel of the robotic sprayer subject to the capacity and edge demands. And what our results looks like, let me give you an example. Like we have a robot start from the depot and then spring the first blue dice line and then turn right to spring the second demand edge, and then if it ran off the agricultural hose, so back to the depot to get refill, and then start from the depot again to spring the remaining demand edges. So this is our problem. And actually our problem is an edge coverage problem. But when discussing edge coverage routing problems, the capacitated arc routing problem is often the first thing that comes to mind. The capacitated arc routing problems consist of finding a set of vehicle trips that must satisfy its vehicle departs from the depot, serves a subset of required edge. Required edge, we also say it as demand edge, and returns to the depot. The total demand served by a vehicle does not exceed the capacity of the vehicle. And then its required edge is served by exactly one vehicle. And the capacitated arc routing problems is anti-HAR problem. And our agricultural spring vehicle routing problem with splittable edge demand problem is also edge coverage problem and anti-HAR. But the difference is we allow splitting the demand on a single demand edge among robots. And then we have developed a mixed integral linear program to address the splittable agriculture routing problem. And we have input data, the non-negative cost equals the distance, or the arc, IJ, and the chemical requirements, and the capacity of robotic sprayers. And the output have two sets of variables, decision variables. The first part is xij to decide it cover this edge, ij or not cover. And yij is the amount of chemical sprayed on the arc. And then we have this model. The objective function aims to minimize the total distance traveled. Constraint 1b restrict the total springs of a robot to not exceed its capacity. And constraint 1c ensure that the amount of springs on each edge is greater than or equal to 0. Constraint 1d guaranteed that the total amount of springs on each edge equals the corresponding edge demands. And constraint 1e, we call it as a link constraint. It means that edge ij can be springed by robot only if it covers edge ij. And the last 1f is the flow constraints. We make sure that the incoming flows of each node equals the outgoing flows. We provide examples here to illustrate the 1F constraints. Like we have a small graph, the depot is here. If without the constraints of 1F, the solution would be like from the depot to 2 and to 4 and then stuck at node 3. So we need the incoming flows of each node equals the outgoing flows. Okay, and 1G is a connective constraints. Similarity, we provide an example here to illustrate the constraints, the importance of the constraints. Like we have dipole here, and a robot start from here to spring the blue dicer line. And if without these constraints, the robot start from dipole and then jump to node 2, and then to 4, and then back 2, and then jump to 6. So it's an illegal route for our problem because the robotic sprayer cannot fly. And we need a complete route for these problems. So it's really important for this for our model to have the connective constraints. But the small problem is for these constraints, we need a huge computation because we need to calculate the subset of n. So if the size of the problem is very big, so we need to calculate a lot of subset. Yeah, and then when it comes to the scenario, if the age demands much greater than the capacity, so in this part, we can categorize the robotic sprayers into 3 different groups: the unused robots, and the robot spraying a single age, we call it a singleton robotic sprayer, and the robot spraying on multiple edges, we can call it a multiple edges robotic. And then we got a theorem here. For any robotic sprayer routing problem, there exists an optimal solution xy such as the number of multiple edge robotics less than the number of demand edges. And the remaining robots are either unused or have singleton robotics. So by using the theorem, we can simplify here. When the scenario age demands greater than the capacity, we can split in two sets of robots. The first part is about the singleton robots, and the second part is about multiple edge robots. So the key idea for this one is just because we can calculate the singleton robots by distrust methods to calculate the shortest path from the dipole to every node of the problem. So if we can calculate it before that, so we can just decrease the number of decision variables. So then we can calculate this problem efficiently to get a solution, right? And then this is the model for large edge demands problem. We make a comparison between the basic model and this large edge demands model. And the graph, we can see from the graph, the x-axis is the time consumption, and the y-axis shows the associated cost. The upper and lower bound of basic and the large edge demand models are represented by the black solid and red dotted lines, respectively. The graph indicates that the large edge demands, which is represented by the red lines, show that the large edge demand model achieves converge rapidly and reach an optimal solution in about 6,000 seconds. But for the basic model, after 6,000 seconds, it still returns a very big gap. So this is say the basic model returns a gap, and the large edge model more efficiently when working at a large demands problem. And actually, we did a lot of different experiments in this part, but I'll only display one of these results. The other results is very similar as this one. And then we want to solve the 2 different models. So there are a lot of exact algorithms to solve this like this kind of routing problem, like branch and bound base and complementary lower bounds problem and the cutting planes and branch and cut methods to solve this kind of problem. But they are limited to small scale problems. So here we are using a heuristic algorithm to compute the upper bound to solve this kind of problems. And so let's move to the next part about methodologies. To solve this kind of MIP model, we are using legit constraints, symmetries, elimination, and heuristic repair methods. And for the legit constraints, the basic idea behind these constraints is to simplify the problem by removing the costly constraints and then reintroduce them if needed. I just mentioned like the connectivity constraints is really costly. So here we can remove the connectivity constraints first, and then if the current solution violates the constraints, we just reintroduce these constraints here. And the symmetry elimination, we are sorting the solution from less costly to more and orienting the route by not allowing the return at the depot to connect to a lower indexed node than the outgoing arc, which can help us to lower down the feasible solution area, so can improve the speed of this calculation. And the last but most important one is the heuristic repair method. And this main idea of this method is based on the infeasible solution, and then we use the infeasible solution to construct a feasible solution and introduce to this whole system, and then we get a better upper bound. So for the heuristic repair method, one thing is we have two sets of decision variables. One side is about xij and the other side is yij. And yij always feasible, but xij should be integer. So sometimes it's fractional or not integer, it's fractional or infeasible. So we can use the variable of yij to construct a feasible solution xij, and then we pass to the solver to solve this problem. It will provide, if it accepted by the solver, it will provide a good upper bound. So this is the main idea of the heuristic repair method. This graph is a comparison results among the different techniques. And the x-axis is the time consumption, while the y-axis is the corresponding gap. And from the graph, we can see that the basic model fails to obtain a solution. But for the other three techniques, they all work to get a solution for this instance. And if I increase the scale of the problem, we can see from the instance age, only the heuristic repair techniques can obtain a solution. The other techniques failed to get a solution. So we can get a conclusion that for the other techniques, they work for medium-sized problems, but not working for large-scale problems. But for these heuristic repair techniques, it works well for a large-scale problem, but has an unsatisfactory gap because in this instance, we return a 14% gap. Actually, it's an unsatisfactory gap. So the future work we can working on to narrow this gap. And okay, and we also make a comparison with a set of classical capacitive algorithm problems data set, and first designed by Barrowand. And this instance have been generated by varying the capacity of the vehicles. The columns N and E are numbers of vertices and edges, and the R is the number of vehicles involved in this problem, and the P is the capacity of the vehicle, and some D is the demands of the demand age, the total demand of the demand age, and LB is the lower bound obtained by the literature, and LBH is the heuristic repair techniques lower bound, and the best known are the best results reported in previous capacity arc routing problem literature, and this heuristic repair technique solution is over this column, and from the graph, from the table, we can see heuristic repair techniques can return a good solution for the set of value 1C, and the other instance is value 2C. It is worth noting that because our heuristic repair techniques allow splitting on one edge among different robots. So that's the main reason why we get a better solution here. And then we also did the parameter analysis. The parameter tau comes from the heuristic repair techniques and represents the number of times the heuristic will be run without improvements before abandoning any other attempts to run the repair techniques. Which is mean from this table, we can see there are about 15 accepted solutions, but the x-axis is the number of tau and the y-axis is the upper bound. We have 15 accepted solutions, but on the last 4 didn't change too much. So because if we contract the feasible solution, it's really costly. So if we just select a tau before the last 4 accepted solutions, it will efficiently to get our solution, because the last 4 doesn't matter in our problem. So the parameter analysis is only about the selection of tau here, and the further discussion about the selection tau is worth studying, because for different problems, the tau seems so randomly. Sometimes we cannot find a function to find what's the tau look like. So the further discussion about the selection of tau is worth in studying. Now I'll make a short conclusion of my previous presentations, previous sections, and the work presents a splittable agriculture chemical sprint vehicle routing problems, and formulate is as a mixed integral linear program. And we are using theoretical insight about the optimal solution structure to improve the formulation. And we provide 2 different formulations. The first one is the basic splittable model, and the second one is the large age demands model. And the solution methods consist of Legge constraints, symmetry elimination, and heuristic repair techniques. And we have a lot of experiments, but the test on instance generated based on the real data shows the basic model is limited to small-scale problems, and the other techniques, for example, Legge constraints and symmetry eliminations, work well on medium-sized problems. And the heuristic repair methods outperforms the other methods on large-scale trees. And moreover, the test results indicate the splittable capacity arc routing problem model could provide cheaper solutions in some instances compared with the classical capacity arc routing problem. Okay, and next, I'd like to talk about some ongoing work. For example, like we have the graph, irregular graph over here, and the problem is spraying the blue dashed line. We can formulate this graph, transfer to a regular single grid graph. And then we can find the solution pattern for this graph in polynomial time. Because for this irregular case, most of the complexity uprooting problem is NP-hard, so we cannot solve it in polynomial time, but we can solve this regular single grid graph in polynomial time. And then after find the solution pattern, it always spring the adjacent row edge, demand edge over here, and then we can develop a path pattern for this kind of problem. For example, if P equals to D, which is means a robotic capacity can satisfy the two demand edges. So in this situation, a solution pattern for this regular single grid graph should be the first robot springs 110 and then back 1, and the second robots start from 1 to spring 2, 3, spring 3, 8, and then back 9, spring 9, 2, and then back 1. And the last robot start from the start node 1, and then go for 5, and then spring 5, 6, back 7, and spring 7, 6, and back to the depot. So this is the solution pattern, and we hope that for the regular case, there can provide some inspiration for the irregular case, and like we can provide a better bound for this problem because we can round to it in this kind of pattern. And for the large scale problem, we can solve it efficiently. And we also work for the multiple layer problem, because for this problem is single layer, means that we only have one layer, but for this complicated case, we have 2 layers. And for this problem, we are working to generate the path pattern for this grid graph. And later, we will apply the pattern to solve like some irregular case. But we cannot sure that it really works for the irregular case, but we hope to give some inspiration or we can get some attributes from the regular case to irregular case. And those are the reference for today's presentation. And thank you so much for your listening.